processing. If you see the boron carbide, silicon carbide, they have a different density. But the boron carbide is the one which has been, used extensively in preparing the metal matrix composite because its density is close to the density of aluminum. So 2.7 is the density of aluminum and grams per cc, and here also it is 2.5. So when you stir and mix two different material having a different density, probably getting a homogenization is a challenge. But probably since there are two material having nearby density, probably it helps you to make a uniform distribution of boron carbide particles in the matrix. It's become little bit easy. So moving further, that how you can manufacture the metal matrix composite with the help of friction stir processing. So say for example, there are various techniques are there. One of the technique which has been referred here, which is called hole method. Hole method is nothing but you develop, under the shoulder region or under the pin region, you develop a blind holes. These are all blind holes, and these holes are filled with the reinforcement. So you have a matrix. Say for example, this plate is nothing but it's an aluminum plate or whatever the substrate material or a matrix material you want. So plate is made up of that matrix material. And then you develop a blind holes of certain diameter and certain depth under the pin region. And then you fill those holes with the help of reinforcement. Say, for example, boron carbide. Once you are done, because this boron carbide is a dry powder, so it is very difficult to fill these holes with those dry powder. So you need to mix with the some carrier solvent. Either you can use acetone and make a certain small slurry, and slurry will be filled inside these holes. Once it is done, you take a tool. That tool is pinless. Now you see there is a tool which is pinless, and then try to, close those channels. So there is we already discussed in the first module, the function of the shoulder is to generate the heat and function of the pin is to mix the material. So you take a tool which is pinless and try to close the channel. Now channel has been closed with the help of, this is called capping pass. Capping pass means what? You are trying to close the channel. Then with the same area will be processed with the tool which has a pin. Now same area which will be, you have a now tool, different tool which has a pin, and that area will be processed with the help of the tool which has a pin, so that the reinforcement and the matrix, they mix properly. And then you will get a metal matrix composite under the pin region. So this is one way of manufacturing the metal matrix composite with the help of FSP. You can go with the hole method, you can go with the slot method. The processing technique remains the same. You need to close, then you need to process, right? So this is hole method, this is slot method, or you can say groove method also. But then the step 2 and step 3 is similar to what we discussed in the hole method. Similarly, there are other two techniques. Say for example, sandwich technique. Sandwich technique wherein you have between the layers, you have the powder. You see here between the two reinforcement, two metallic sheets, right? You have a reinforcement, and with the help of direct FSW tool, right? You can, develop the metal matrix composite. And the fourth method, wherein you can put the powder directly on the surface and you can develop a surface coating method with the help of FSW, FSP tool. So these are the four techniques. Among all four techniques, the technique which we discussed like hole method and the slot method, these two methods are extensively reported in the literature for fabrication of metal matrix composites through FSP route. And to be very precise, this is called surface composites. Why it is called surface composite? Because we are developing the composite only in the surface. Whatever the depth of the pin you have, right? Say for example, 3 millimeter, 2 millimeter. So you will get metal matrix only under that region, 2 to 3 millimeters. If you have a plate which is of 6 millimeter and a pin length which is of 3 millimeter, you are getting a metal matrix up to depth of 3 millimeter, while remaining 3 millimeter will remain as it is. So you have a sandwich property. Your core will remain tough and ductile, while the surface will have a very good hardness and the wear property. So this is called sandwich property you are getting with the help of friction stir processing technique. Now let us look at the actual way. So here there is a small animation which probably help us to understand the process. So you take a plate, aluminum plate, for example, create the blind holes, and these blind holes are filled with the reinforcement. Then you try to close these blind holes with the help of a tool, and that tool is nothing but it's a capping tool. You don't have a pen here, right? Then after capping, again the same area will be processed with the tool which has a pin. So this is called stirring tool, or you can say stirring pass. So this is how you can manufacture the metal matrix composite. So this is one of the application of friction stir. I mean, this tool can be used for friction stir welding also. I mean, the tool which you are observing for this tool can be used for welding also, right? But with the same tool, you are doing a processing. So you can manufacture the metal matrix composite with this technique, wherein you can see in the hole pattern technique has been used. You can see here the actual the pattern. So the zigzag pattern, you can see here the size of the hole, the depth of the hole, right? How much amount of the volume fractions that you are adding here, that is also very, very important, because finally the property will be governed through the volume fraction which is being added, right, in the during the process. So these holes will be filled with the reinforcement, and then you apply a capping pass, then you apply a stirring pass, and the number of passes also is a parameter. Same area you can do stirring 1 time, 2 time, 3 time, either in the same direction or either in opposite direction, so that you can ensure a better mixing of reinforcement into the matrix of material. So moving further, you can see here there is an initial feasibility which was done in our laboratory, wherein you can see the whole pattern which has been created with the help of very simple drilling machine. Then you fill those things with the help of reinforcement. Reinforcement is mixed with the acetone and it has been applied with the help of paintbrush. And then you can see the capping pass has been done, the stirring pass has been done. So that reinforcement has mixed with the aluminum metal matrix. So this is how it can be done. Now, after applying this stirring pass 1 time, you same area can be, same area will be processed with additional stirring passes also. Say, for example, you have done one stirring. Now, same area you apply second stirring, you apply third stirring. With additional number of stirring passes, you are trying to mix more, you are trying to ensure that the powder should mix more uniformly into the matrix, right? So that there should not be any agglomeration of the particles, and there should be uniform distribution of those reinforcement particles into the matrix of aluminum. So this is how you can see one more picture. I mean the scanning electron microscopy picture, and which shows that when you go for a friction stir processing, right, these reinforcement particles, say for example, in this case, they are boron carbide particle. So these boron carbide particles, they themselves also get fragmented, right? You see, some particles are very fine, some particles are bigger. Say for example, if you have started with 20 micron particle, those particles, they also get fragmented because you are doing a processing, you are doing processing 1 time, 2 time, 3 times, right? So those powder particles also get fragmented. At the same time, your matrix, which is of aluminum, so matrix has certain grain size, so the grain also get refined further and further. So the final property is nothing but the final tribological property. What you are getting is nothing but is a combination of the property of the matrix, I mean the refinement of the matrix, and the reinforcement particles which you have added. Those particles also get fragmented further, and the most important, it's uniform distribution. The powder particles should be uniformly distributed in the matrix. Then only you will get a better metal matrix composite through FSP route. So that was the first element. Now, after spending little bit of time on surface composite, now the another important element of another different application of friction stir processing, which is called superplasticity. Now, what is superplasticity? Through the diagram, you can make out the superplasticity is nothing but ability of metallic material to exhibit uniform tensile elongation. Uniform tensile elongation 200% and more. Now, this is very, very important. So you take a aluminum plate and then you run through friction stir processing tool. So the grain refinement will take place. Say, for example, to help you out with the elementary understanding, you see there is your normal tensile specimen. And then when you deform the specimen after friction stir processing, right, your material if display this kind of elongation, right? Or maybe this time kind of elongation, you see 390, 1050. If the material display this type of elongation, right, then you can say your material has superplasticity, right? So this superplasticity also can be achieved with the help of friction stir processing. So when you go for a friction stir processing, we talked about one which is used for surface composite manufacturing. Here we are talking about plain superplasticity. Plain superplasticity means what? We are not adding any reinforcement. We are just use the FSW tool or FSP tool to refine the metrics, right? There is no any additional reinforcement here, right? So with the help of this concept of FSP, you can, the grain refinement will take place. That is one, because you are running the FSP tool. Additionally, your grains become equiX, right? Additionally, the third important thing, because since aluminum, you have some precipitates, right? So these precipitates, they are of different size and different order. But after FSP, these second phase particles, right, they become very fine. I mean, they also fragmented with the help of FSP, right? And after that fragmentation, right, they uniformly distribute into the matrix. And with the FSP, your grain boundaries, which will be of higher angle grain boundaries. So these four attributes, reduction in the grain size of the order of less than 15 micron, equiX grain size, presence of fine second phase particles, right? And the fourth one is a high angle grain boundary. These four important factors, right? These four attributes leads to this kind of deformation, which is called superplastic behavior of the material. And this can be achieved with the help of friction stir processing. So this is another area of research wherein a lot of work is going on in that particular domain also. Now you see some of the actual pictures of, say, for example, 7075 material, which you can see here, right, which is as machine. That means there is no processing has been done. And then after friction stir processing, right, you can see at certain strain rate and at fixed temperature of 490 degrees centigrade, the temperature is fixed, right? You can see the strain rate, it is getting changed, right? 1 into 10 raised to minus 1, 3 into 10 raised to minus 2, that's how. And you can see here, you are getting a elongation, very high degree of elongation you are getting after friction stir process, right? So this behavior, what you are observing, right? I have explained you with the schematic diagram and why you are getting this behavior because of the following reasons. With the FSP, the grain refinement will take place. Grains become equiX. Second phase particles also uniformly distributes and they inhibits the grain growth and you will get large amount of the higher angle grain boundaries. And these higher angle grain boundaries are very, very important compared to low angle grain boundaries because they resist the deformation. So this is what the concept of superplasticity, which can be achieved with the help of FSP. There are many techniques. Please understand. There are many techniques are there to achieve superplasticity in metallic material. There are, right? So this is FSP has been explored and it is found that FSP is more easy to apply to get friction stir superplastic behavior in metallic material. So when you say superplasticity, now you are all familiar with what is friction stir welding. So you are familiar with the friction stir welding parameters also. So if you look at those parameters, right, we discussed in the first session also that when you go for a dissimilar material, what are the important parameters? When you're working with similar material, what are the important parameters? So here in FSP, FSW, right, even if you work on FSW, the tool material, the tool geometry, right, I mean, people are exploring what different pin geometries also. I mean, they are working with different pin geometries starting from triangle, square, pentagon, hexagon, right? Cylindrical, taper, with thread, without threads, right? So depending on the base material, your tool material also will be different. At the same time, the machine variable. I mean, machine variable includes what? Your RPM, your feed, your tilt, your backing material, right? They are all machine variables. Then multipass. As I explained you, same region you are processing with single pass, double pass, triple pass. That is called multipass. And maybe in the same direction, maybe in opposite directions. So at the same time, you see that there are a lot of work has been done in active cooling. I mean, if you remembered in the first module, we talked about assisted heating mode. Assisted heating mode, we apply extra heat, right? And extra heat can be applied with the varieties of the heat source. But here, there is a term called active cooling. So active cooling will help you to reduce the grain size, right? Instead of achieving the higher peak temperature, with the active cooling during the FSP. I mean, you can do cooling with variety of the sources. Researchers have done with even liquid nitrogen also. Researchers have tried with the compressed air, even with the CO2 also, and maybe with the submerged cooling as well. So these active cooling will help you to reduce the grain size and may help you to achieve a better superplasticity in the material. So tool material, tool geometry, shoulder profile, all these things are very, very important parameters in getting superplasticity. So here, you can see here, this is a slide which probably helps you to understand the mechanism of active cooling approach, because that is slightly unique in the sense. Say for example, when you go for a heating will come ahead of the tool. When it comes to the cooling will come back of the tool. So after the processing, you are cooling it faster, right? With the help of cooling medium like air, water, CO2, liquid nitrogen. And you can see here, this is the coarse grain structure what you have initially, right? And after the FSP, you can see the coarse grain become fine grain. So this is one of the requirement. It should be less than 15 micron. At the same time, they are uniformly distributed, right? The third, you have a high angle grain boundaries. Fourth, the precipitates also should be uniformly distributed. So this behavior may lead to a higher elongation in the material. And this behavior is termed as superplastic behavior in the material. So as I mentioned, surface, you can do friction stir processing. I mean, the first one which we understood, which is for composite manufacturing, wherein you are adding reinforcement. Here you are not adding any reinforcement. You are simply uh, processing the material without any adding the reinforcement. You are playing with the parameters and trying to achieve the fine grain structure. So friction stir processing can be done two type. I mean, surface FSP and volume FSP. If the length of the pin is exactly the matching with the thickness of the plate, you can say it is volume FSP. And if you are doing say only on the surface, just 1 or 2 to 3 millimeter from the surface, it is surface FSP. So depending on the length of the pin, it has been termed as surface FSP and volume FSP. The idea, depending on your need, right? You can do surface FSP and volume FSP, and this will help you to improve the formability behavior of the metallic material. So the mechanism I have already explained you that the first, which is the grain refinement. Because of FSP, it generates the fine microstructure. EQX recrystallized grain, right? You have seen in the diagram, in the earlier diagram, you can see the fine grain structure which you, right? And with the help of this FSP, this will help you to either increase in strain rate or decrease in the temperature at which the superplasticity is achieved. Because industry, they are looking for high strain rate. Deformation should be done because they have a production requirement. So the strain rate should be high, and the temperature at which you are achieving the superplasticity, the temperature should be low. So if you can, this is what is the industry is looking for. Higher the strain rate and the lower is the temperature. The grain refinement induced by dynamic recrystallization within the nugget contributes to increase in the hardness and other mechanical property also. It also helps you to improve, FSP also helps you to improve the formability, ductility, the fatigue resistance, right? Why it happens? Because before FSP, you have those large precipitates. Now after FSP, what will happen? The grain also get refined, right? Those large precipitates, they get fragmented and they become a fine precipitates. And these fine precipitates act as a barrier to the dislocation motion. And this uniform EQX fine grain structure is also essential to enhance the material superplastic behavior. So these are the mechanisms which are responsible for improvement in the mechanical property as well as in the metallurgical property which we have discussed. So as I mentioned, friction stir processing can be reported. It was also reported for castings, because if you see the aluminum castings, they contain a lot of porosities, segregations, right? Segregation is what? The non-uniform distribution of chemical compounds. You have an inhomogeneous microstructure, right? So you will get improve. I mean, you will get poor properties. Now, with the help of FSP, right, you can locally refine the microstructure and eliminates the casting defects at selected locations where the property or where you want a property improvement could enhance in the part performance, or the service life. So these are the benefits you will get. Means people have tried FSP as a tool in castings, superplasticity, and even for surface composite manufacturing. So this is the mechanism I have already explained you that, but still the mechanism is why you are getting improvement in the property, right? In FSP is the mechanism is that when you have the precipitates, right? So precipitates, they are all intermetallics. Now these precipitates are not that much capable to deform than the matrix. Matrix is very soft. Matrix is soft and precipitates are harder. So what will happen when you start deforming this material? The deformation behavior of the matrix is different. Deformation behavior of the precipitate is different. So the chances are that you may get some cavities in the material and there is a disconnect of matrix or the rupture of the precipitates. So FSP allows the breakage of large precipitates and dispersion in the homogeneous matrix and increase the material's tolerance to withstand the deformation. So this is what the crux of the matter for why FSP helps you to improve the property because of this reason, right? So finally, now let us come to the third module of friction stir processing. The first module which we talked about is FSP for surface composite manufacturing. Second was FSP for superplasticity. Now the third one is friction surfacing. So before I start, I would like to show you a small clip here. Is the clip is running properly?
Yes, sir.
Okay, okay, fine. So you can see here, this is the third application of friction stir processing part, and it is different compared to the other two modules. Different in the sense that here you have a tool, or you can say a rod, which is a consumable in nature. Means it get consumed during the process, right? It is not like a non-consumable FSW tool. And then with the help of friction surfacing, you are trying to clad the surface. This particular rod get consumed during the process. It will clad onto the surface. You see, initially it is like a tapered pin kind of thing. And then you can see immediately the deformation starts and it is getting clad onto the surface. So this particular process, which is called friction surfacing. Now you see here, there are four different steps which are shown here. Step number one, you require a rod, and this rod is a consumable as I mentioned, and you may have a different material combination, maybe similar material combination, dissimilar material combinations, right? Ferrous, ferrous, non-ferrous, non-ferrous, ferrous, non-ferrous, any combination. So you can see here there is a rod which will rotate at certain RPM, and then you bring in the contact with the substrate. So there is an initial contact. So initial contact is there. Once the initial contact is there, now you see there's a deformation starts. Once the deformation starts, you see, right? Because the rod what you have is under certain force also, and it rotates at certain RPM also. So the diameter of the rod, the length of the rod is also very, very important. And then when the substrate starts moving, you can see the clad layer deposited on the surface. So this is the actual picture. You see the actual picture? I mean, there is a rod, consumable rod having certain diameter, certain length, and then you bring in the contact with the surface, right? Once you bring in contact with the surface, you see that the rod will start deformation, rod will start deforming, and you can see here, and then you can see once you apply the feed to the substrate plate, you see it is getting deposited onto the surface. So this is called friction surfacing. This operation called friction surfacing. Sometimes it is also named as solid state cladding. This process is mainly for short length application. Why it is only for short length? Because your rod is a consumable. It has a certain length. It has a certain diameter. Once it get consumed, yeah, you need to go with the second rod, and then you can try to cover right, left, top, bottom, whatever you want. The additional rod you need to put in, then only you will able to cover more area. So whatever the width which you are observing here, which is called bead width, this 22 millimeter which has been written, it is called bead width. But when you cut the cross section, right, then what will happen? That at the interface, the bonding will be less than even the rod diameter. Say for example, your rod diameter is 18 millimeter, right? And what you are getting deposited here is close to 22 millimeter. But when you cut the cross section at the interface, the bonding will be less than the diameter of the consumable rod, 1 or 2 millimeter less. So there is a term called bead width and bond width. What you are observing 22 millimeter, which is called bead width. And when you cut the cross section, when you study metallurgical bond at the interface, which will be less than the rod diameter, it is called bond width. So bead width and bond width. Please remember these two terms. So this is the process, as I mentioned. The first, there is a consumable rod which will rotate at certain RPM, and then you brought in the contact with the workpiece under the certain axial force with the stationary substrate. And after initially rubbing period, right, you can see there is a plasticized layer which is forming under the consumable rod, and then the substrate traverse has been given. So consumable rod, I mean, getting deposited as a layer, and so this deposited layer, microstructure is similar to the hot worked microstructure with zero dilution and very strong bond with the substrate. So so as I mentioned, this is I already explained you the width and thickness of the deposit layer is very important, and it is getting influenced by the material combination. What is the rod material? What is the substrate material, right? And as I mentioned, the bead width and bond width, there are two important parameters. And bond width will be what you are observing 22 millimeter, which is called bead width. But at interface, what you are observing is a bond width, which will be less than the rod diameter. So there is always lack of bond associated, right? Now, so these are the important parameters which will control the entire friction stir surfacing process. So if you see the process parameters, right, material property is one parameter. I mean, what material you are taking, the rod material, the rod diameter, base plate material, base plate dimensions. Similarly, the geometry, rod diameter, rod length, thickness of substrate, the clamping, the backing plate, right? Then the process parameter, whether you are doing with external gas, environment, external cooling, external preheating, right? All those things. And then finally, whether your system is a feed system, I mean, force-based system or a feed control system, right? This is also another important parameter. And finally, all together, the geometry of the material, material property, the process control, right? It will affect on what? The cross section, the thickness and the width and the bonded width, thickness of the bead, width of the bead, bonded width, surface finish, roughness, oxidation, and the I mean the bond strength, right? Tensile shear, bending, and the performance in terms of the heat generation, deposition efficiency, residual stresses. All those things are important in friction surfacing. So this is what a diagram which may probably helps you. So if you see from the top, you can see, say for example, 22 millimeter. But when you see at the cross section, you see there is a lack of bond on the right and left, right? So there is always lack of bond at this. You are getting a bonding only under, if you see the rod diameter, maybe 18 millimeter. So you are getting slightly less than the rod diameter. And a material which you are depositing, I mean, say for example, if you are depositing aluminum, right? Aluminum is very soft, magnesium is very soft. In one go, the thickness which you are achieving may be close to 5 to 6 millimeter. But as you move on to the high strength material like steel and stainless steel, the thickness which you are getting in one pass may be close to 3 millimeter. In case of high strength materials, further high strength like nickel based alloy, stellite alloys, wherein the thickness in one go may be close to 0.5 to 1 millimeter. So please understand, different material, they have a different strength, different melting point, right? And so soft material deform more, and the thickness which you are achieving in one go may be higher order, 5 to 6 millimeter. As you approach the high strength and high melting point material, the thickness which you are achieving in one go may further go down. So you can see here, this is one particular diagram which shows you, because here you have a rod which is consumable in nature, and when you are depositing, there is a downward force like friction stir welding, there is a z-axis force. Now this force is very important. Say for example, if you see 2 kilonewton, right, for a given material combination, there is no, consolidation. You can see there is a entire length, there is no bonding at all. So you need to further improve from 2 kilonewton to 3. Some bonding has happened. 4 kilonewton further improved, right? So if you go to the 5 kilonewton, it is best. You have still lack of bond at the right, I mean, both the extremes, right? But if you go beyond 5 kilonewton, you see the shape has changed, right? So you need to ensure that for a given material combination, you need to improve the downward, you need to optimize the actual force so that you will get better, this terminology, which is called bond width. What you are observing here, it is called bond width, right? And what you are measuring physically, which is called bead width. Similarly, as your travel speed increases, I mean, substack is going to move, right? As your travel speed increases, what will happen? Your coating width will go down. The thickness of the coating also will go down, right? As in arc welding processes also, as your welding speed increases, what will happen? Your reinforcement will go down. Bead width will go down, right? All these things will, because your heat input is also decreasing. Similarly, here also, the width of the bead which you are depositing will go down. Coating thickness also will go down with increasing the travel speed. And this is something which is very, very interesting from metallurgical perspective, that when your welding speed, I mean, your traverse speed increases, right? You see that your as the traverse speed increases, first you focus on this slide, I mean this particular graph, and traverse speed increases, you see that your interfacial bond strength also increases. Now interfacial bond strength increases with increasing the traverse speed, right? The higher the traverse speed, right, higher is the interfacial bonding strength, which we are discussing. And at the same time, you see that higher the interfacial bond strength, you see at a higher speed, the failure is in the coating. If you go with the lower traverse speed, right, lower traverse speed, you are putting a lot of heat, and since you are putting a lot of heat, right, there are a lot of intermetallics will form, right? And because of extra heat, you see that the failure is at the interface. So you need to improve your travel speed also, so that the failure in the coating is advisable instead of the failure at the interface. So travel speed is also very, very important. The downward force is also very, very important, as I explained. And the last is the rotational speed. I mean, the RPM at which the rod is moving. You see here, your rod, which is say 600, 800, 1200, right? Different RPMs you can see here. And different RPMs gives you different finish. I mean, you see 600 gives you very rough finish and very wide. And as the RPM increases, the width will go down. The finish is also improving. So this is another important thing which you need to understand, that how RPM is affecting, right? The friction surfacing process. Because more the RPM, more is the centrifugal force. And because of the higher centrifugal force, right, the material transfer efficiency from the rod to the substrate, which is getting deteriorate. And that's how the bead width is also decreasing with increasing the RPM. And the finish is improving further. And as I mentioned, this process is not suitable for long length application. It is mainly suitable for a short length application for repair and maintenance purposes. So this is what is been there in the literature, that friction surfacing is been reported even for turbine blade repair also. You know, turbine blades sometimes because of corrosive environment or some sleet in the material, I mean, there you may get, especially in hydro power plants. So those getting turbine blades damage can be repaired with the help of this cladding operation. At the same time, you can use this type of short length cladding operation for agriculture tool repair also. And the most more important application, why there is a need to clad aluminum on steel for corrosion application, mainly for shipbuilding app, wherein you have, ship will remain in corrosive environment or a sea water for a long period of time. So that time you need to clad those sensitive areas with the help of uh, aluminum cladding for a better improvement in the corrosion property. So if you look at this friction surfacing, so friction surfacing is a process which is also been reported for additive manufacturing. We all know additive manufacturing is layer by layer. So you can go like, if you can go like this, then friction surfacing is been termed as friction surfacing for additive manufacturing. You can see single layer on the same track, you are adding additional layer, one, two, three, four, right? And multi layers has been, and you can have a different material also. Layer 1 may be of aluminum, layer 2 may be of copper, layer 3 of magnesium, layer 4 may be of other material. So you can develop functionally graded material with the help of solid state cladding or friction surfacing. You can see here 1, 2, 3, 4. Currently in the picture, it has been shown with the same material. So this is called friction surfacing for additive manufacturing. You can say single track, multi-layer. Track is one. and then there are multi-layers. Similarly, you can go for multi-track and multi-layers also. You can see here, if you want to cover more area onto the flat surface, right and left, right, then you can go with multi-track. Instead of creating one track, now you are creating track on the right also, the left also. After creating multiple tracks, each track is been added with additional layer. So this is called multi-track, multi-layer also. So friction surfacing can be used for additive manufacturing applications also. And there are two more configuration, as I mentioned, single track multi-layer and multi-track multi-layer. These two things are also possible. Now, moving further into this particular domain of friction stir processing, the fourth important module, which is called friction stir additive manufacturing. So we already talked about friction stir welding, the friction stir welding variants also. Now, how friction stir welding can be used for additive manufacturing? Just now in the earlier slide, we discussed that friction surfacing can be used for additive manufacturing. Additive manufacturing is what? Layer by layer deposition. So you add one layer, then other layer, and third layer. So if you see this friction stir additive manufacturing, so friction stir welding, the technology which we discuss now, currently we are discussing the processing part, right? We started with friction stir processing. Similarly, we discussed friction stir welding also. Friction stir welding, friction stir alloying is also possible. Friction stir brazing, friction stir cladding, right? But our now discussion is on friction stir additive manufacturing, which is there in the, so layer by layer deposition. Now, your raw material, additive manufacturing is what? Layer by layer deposition, either of same material, maybe of different material. So here, now you can see. So our focus is this. What we have discussed so far, you can focus on this small animation. We discussed friction stir welding, wherein you are joining the two material, either same material, dissimilar metals with the backing, and you join them. So this is called butt welding, which you are doing. But instead of that, if you can go with the lab configuration, say for example, first you go with layer 1 and layer 2 and join them. Then followed by layer 3 and layer 2, then join them, and layer 4 and layer 3, then join them. So this is how each color code indicates they are of different material. They, black is different, orange is different, green is different, gray is different, right? So they are of different material. And then because they, say for example, in fusion welding, it is difficult to join dissimilar metals if they are metallurgically not compatible. So you are left with only the option of friction stir additive manufacturing or friction stir welding or friction stir processing. So instead of joining the material in the butt configuration, now you are joining the material in the lab configuration. First you need to, now you see the cross section. This is layer 1 and layer 2. So the tool penetrate from the layer 2 and it joined the layer 2 and layer 1, right? Once layer 1 and layer 2 is done, you add layer 3. Then tool penetrate from layer 3 and it go to layer 2. Then you can go to layer 4 and then it penetrate to layer 3. So that's how you can go for friction stir additive manufacturing. So this is the offshoot of friction stir welding, which is called friction stir additive manufacturing. You can see here there are different kind of functionally graded material which has been which can be manufactured with the help of friction stir additive manufacturing. You can see here there is a sandwich structure. Sandwich structure means what? I mean, you are familiar with the sandwich. So the top and the bottom layer is same. In between, you have a different material, right? You can go like this also. Top and bottom is different, but internal layers are same, right? So you can see this kind of structure, which is called sandwich structure with the gradient. And you can go with alternating gradient structure also. 1, 2, 1, 2, you can see this kind of thing. And you can have a fully gradient structure also. I mean, all four layers are different, as you have seen in this diagram. See, layer 1, layer 2, layer 3, layer 4, they are different. Don't go with the impression that all four layers you are joining in one go. First, you need to go with layer 1 and layer 2. Then you remove the flashes, if at all flashes are there. Then you put layer 3, then layer 3 and layer 2, then layer 4. And that's how you can make this type of gradient, alternating gradient material. Friction stir additive manufacturing. So you may have a question that what are the applications of this type of gradient material? So these gradient materials, they are different and sometimes it is difficult to join through fusion. So especially in aerospace industry, component requiring like stiffener and stringer, mechanical property can be manufactured using friction stir additive manufacturing. You can see here, these are the gradient material which you can see here, one, two, three different layers, and flatten the skin panel of fuel sludge. At the same time, you can see here also, one, two, three, four, right? And you can see the complete schematic diagram where exactly you are going to fit them, right? So here you can see the flange, you can see the rear spar, and the vertical, you can see this, I mean, one, two, three, what you are observing, one, two, three kind of thing, right? So these are the some applications they are exploring with the friction stir additive manufacturing. So moving further into this domain, there is a so last process was friction stir additive manufacturing. Moving further, there is a process called friction stir forming. We are all familiar with the forming operations, metal forming operations, but how friction stir welding technology can be used for friction stir forming. So here there is a schematic diagram which may help us to understand the process. So the first you can see there is an anvil and you have a stir welding tool. Now between the anvil and the stir welding tool, you have upper sheet and lower sheet. Now you see here, the lower sheet has the cavity, right? And when the upper sheet, I mean, a stir welding, friction stir welding tool, which brought in the contact with the upper sheet, and then it slowly deformed the upper sheet material, and then you can see it will take a shape of the what you have in the cavity. And then when you eject, you will get this type of assembly, right? So this is called friction stir forming. So principle of behind the friction stir forming process is that the rotating tool hits the upper sheets to a plasticized condition. And when the rotating tool plunge into the upper sheet, it generates the frictional heat, which makes the material to form into a cavity for lower sheet. So this particular operation, which is called friction stir forming. So you, because in metal forming, you are familiar with the term called metal forming. So this is also, you can see it has been reported in generating the multiple fins also. Researchers have tried that how friction stir forming can be used for generating the fins. You can see the fins here, right, at the different travel speed, right, which has been there. So these are some applications. So new variants are coming up with the how this solid state domain can be further expand in the different applications. So if you look at the challenges and applications, friction stir welding is again, I mean, with reference to my earlier talk and this talk, you can see friction stir welding of high strength material, as I mentioned, you need to go with some additional preheating. And why friction stir welding of steel and stainless steel is not, it is very difficult because the flow strength is very, very high. So with the additional heating, you can reduce the strength of the base metal and then stirring and mixing become easy. So especially friction stir welding of titanium, steel, stainless steel, nickel based alloy, right? So there are challenges with reference to the tool material and high temperature and the force requirement. So one should try to see how this technology can be developed for more economically it can be developed for this material. Before I come to an end of this talk, I would like to mention here that there are some learning and future direction that, you know, we always think that metal joining. So we have done with the friction stir processing part, right? Now that topic is over. And what are the learnings from the earlier module and this module? That we always look from a perspective that the welding for metal joining. Okay, that's the primary function. But with the help of welding processes, you can do repair and maintenance also, right? You can do cladding, hard facing, and spraying also. And researchers are now exploring there are different welding processes for additive manufacturing. You can see here, say for example, welding based additive manufacturing, a lot of work is going on, right? So here to give you some more glimpse in this particular direction, you see that all welding heat source. I mean, you see for welding, you require all arc welding processes. Arc welding includes TIG welding, MIG welding, plasma, submerged arc, right? All these kind of heat source which are there. Laser is one of the most important as far as additive is concerned. So these are the common heat source we have already explored extensively for welding application. Now these heat source, nowadays researchers are working to explore for additive manufacturing. And there are many technologies which are already in the commercial level. Say, for example, laser powder bed fusion. Now, this process has been there. So similarly, what I wanted to tell you is that welding and additive manufacturing, these two fields, they go hand in hand. The understanding of metallurgy, understanding of the welding processes and its heat source. So whatever the experience which has been earned or developed in welding technology or welding science and technology, right? That can be easily integrated into the rapidly expanding this field of metal additive manufacturing. So this is one part which I wanted to mention here. And to strengthen those statements, now you see here there is a slide which gives you some idea about the welding. You're familiar with MIG welding, you're familiar with the TIG welding, electron beam, laser beam, right? All heat source can be used for layer by layer deposition. Now you see here with the help of laser also, there is a laser beam, the wire feeding, you go layer by layer. The electron beam and wire feeding, you have a, say for example, gas metal arc welding system, consumable electrode you can go layer by layer. Similarly, you can go with gas tungsten arc welding. You have an external wire feeding system, cold wire, hot wire, right? So this is arc welding base. I mean, arc welding processes are used for additive manufacturing. Similarly, we discussed some of them, the solid state welding processes like friction welding, friction stir welding, friction surfacing, right? And there are many other like ultrasonic welding. They are also being reported for additive manufacturing. So here also there is a possibility of exploring these processes for various engineering applications. So one part is use of arc welding processes for additive manufacturing. Another part is use of solid state welding processes for additive manufacturing. And the third is that since it is a topic of, welding, so we always talk that welding of metallic material, welding of casted product, extruded product, but now there is a need to go for a welding of additively manufactured component also. Say, for example, you manufacture something through additive manufacturing, and the component which you have manufactured is a part of some other component, and the other component is already manufactured either through casting, either through extrusion, either through the wrought product, right? So you should have a joining process which talks about a joining of, say, for example, printed to wrought, printed to cast, printed to printed, right? So there is a need for research in this particular domain also, welding of additively manufactured component. And why there is a need? Because of the following reasons, as I mentioned. So the very limited work is being reported and number of articles published in these particular domains are also very, very limited till 2023. And if you see, because of this large chamber you may go, but then you need to store more material and it may cost you also. Printing time also will be more. At the same time, the large size of object may lead to a failure of component during printing also, right? So these are certain challenges. So there is a need for you that you cannot manufacture anything and everything with the printed process, but there is a need for you to go for joining of printed components also. And the last is like we talked about additive manufacturing. Now, additive manufacturing is for additive applications, complex objects, all these things. But additive manufacturing processes can be used for development of transition joints also. In the conventional way of transition joints is like a friction welding process, explosive welding, friction stir welding. These are the processes which are there for transition joints. I'm sure most of you know what do you mean by transition joints. So these transition joints, right, uh, you have to manufacture in the shop floor and then you go to the site and weld them in the site. And if you go with the conventional way, you see here, there is a very long process. Say, oh, you want to join carbon steel to stainless steel. So you can achieve that only with the help of intermediate layer. The nickel butter layer you need to put, nickel filler you need to use, right? Then only this joint will able to survive in the uh, those conditions, high temperature, high pressure, those conditions. So this butter layer is to be, so there is a long process, right? But instead of developing this type of transition joints, right, you can go with the additive manufacturing and you can develop a transition joints wherein you have a gradual change in the chemical composition instead of a drastic change in the chemical composition. So this will help you to you know, save, I mean, uh, face many metallurgical challenges which you are facing through a conventional route. So additive manufacturing can help you to develop this type of transition joints also. So this is slightly typical in nature, but still I thought of sharing with all of you. Maybe some of you might be interested in doing research in use of additive manufacturing for replacement of conventional transition joint with the transition piece. So this is a method through which you can develop a transition piece. You can use GMAW process, you can use laser process, you can use powder process also. And then you can develop a functionally graded material. And gradually it is changing instead of a drastic change. If you go with the welding process or other processes, there is a drastic change in the chemistry. Instead of that, you use functional graded, so you use additive manufacturing to develop a transition piece, right? And then transition piece after manufacturing, you can go for a heat treatment and it will save a lot of your problems, solve your lot of problems, right? And site welding become easy for this type of operation. So this is about the future direction and learning, future direction and some of the learning which I have mentioned here. And before I close my talk, I would like to mention here that, in the beginning, I have mentioned that IAW and PDU, we have signed formal MOU. And now this research infrastructure, all the facilities available, is available across the India for all research scholars, faculty, students, right? And industry also. So this MOU was signed, last year in the month of August, so about 1.5 years back. And this MOU, which you can see here, I think many of you may be knowing that there is a term here, it is written, Dvek Ekam. You see there is a arc, arc leads to the spark, right? And there are two plates. You can see the one plate and another plate, right? So Dvek means there are two elements and Ekam, do ko ek karna hai. So two converted into one with the help of arc. And Dvekekam is a Sanskrit term. So this is what is the meaning of this symbol. And the university PDU and the reservoir of knowledge. So this MOU was signed, and there are some facilities which I have mentioned that we have a dedicated friction stir welding facility available in our lab. Similarly, we have a three-axis automatic vertical milling machine for friction stir welding and its application. Friction stir welding, this one machine will take care of a lot of your application. You can do friction stir welding, friction stir processing, bobbin tool friction stir welding, assisted heating, all kind of work can be done very easily with the help of one machine with the minor change in the tooling part and the frictioning part. You can develop this type of. So this is a solid state welding setup, you can say. You can do friction welding also on this. Then there is another machine wherein you can see, which is used for mainly for surfacing, friction surfacing applications, right? You can do cladding of aluminum on steel with the help of this machine. There, as I mentioned, we are also working in assisted heating. So assisted heating in similar material, assisted heating in dissimilar metals, right? So this is one. Then another one is a hot wire GTW system, right? Wherein, as I mentioned, you can use any arc welding heat source for welding application. I mean, for additive manufacturing applications. So this is you can see here, there is a main power source, then filler power source, wire feeding system, then device to move the torch in X, Y, and Z direction. Then you have ultrasonic welding system for metals and plastics. You see this is for metals, this is for plastic, this is a generator, this is a display, and this is a stabilizer. A lot of work is going on. This is in terms of the characterization facility. We have a, VR testing facility in our lab. I mean, pin on disk. We have it's a computer control system. You can do dry, you can do wet, you can do pin heating and furnace heating also. All different modes can be done in one machine with the additional attachments. This is more close-up view of the VR testing facility, right? Where exit. So you can see the disk, you can see the pin holder, you can see the LVDT sensor, the load cell, right? And you can see the fulcrum. So this is the complete wear testing tribology lab. And you can see that with this is a dry condition module. You can see the lubricated volume. You have an extra chamber, right? You need to close the cavity so that the pin on disk, now currently it is open. For wet condition, you need to close it. For high temperature, you need to add on the furnace, right? So, and then there is a interface wherein you can set your parameters for wear testing in all four modes. Then we also have another system which is called dry and slurry abrasion tester. This is about a new system which has been there, and mainly for cladding application. We can test them as per the ASTM standards, abrasion and slurry. Then, as I mentioned about high temperature tensile testing, this is another system to study the superplastic behavior of the material, right? You can see there is a furnace, attached furnace. You can see the pull rods wherein you can mount the specimen, and there is a computer to control the machine. And then this is something which is very unique and dedicated for metal additive manufacturing. We have a laser metal 3D printing facility available on our campus, installed by our Honorable Director General Sir, Professor Sundar Manoharan Sir. And this facility is available for students, researchers, faculty, industry, to explore the additive manufacturing in energy, healthcare, automotive, aerospace. So this facility is there, and this has been there since more than 3 years by now, and to support the Atmanirbhar Bharat initiative to provide the skill set in the area of additive manufacturing to the students, faculty, and the research scholar. So you can see here there are some of the complex objects which has been manufactured. You can see additive manufacturing is mainly wherever there is a complexity, difficult to manufacture with the conventional manufacturing process. You can go with the additive manufacturing. And so this is a machine which you can see. And this machine has a built volume of 150 by 180 millimeter, right? So here there is a working chamber wherein you can print the component. And these are the complex object what you are observing can be printed. So before I stop, I would like to mention about IIW. I've already given you the presentation of IIW PDU Welding Research Center. These are the facilities available, and you are all invited to visit the facility. You are all invited to collaborate with us in case if there is a need for you. And for more information about IIW, please feel free to visit the website iiwindia.com, wherein you will get complete information about the professional body. So the purpose of this MOU is to carry out the research in the field of welding technology and material, to provide the facilities for research for students like BTech, MTech, PhD level, support industry for solving the welding related problem, better industry academia connect, and develop new welding process consumables, right? So this is the purpose of MOU. And IW will help us to strengthen this infrastructure. Whatever the facility which you have seen is currently is through the funded project through the university funding. Now, IIW will help us to strengthen this infrastructure further. So here there is a glimpse of picture wherein 17 August last year, the MOU was signed, and wherein then President of IIW, Mr. Deepak Acharya, and our Honorable Director General, Sir, they had signed MOU in presence of the school director, department head and the dean. Uh, and there are other IIW officials also attended the program. And here, I don't know how much time I have. Yeah, I have a small clip for all of you, but I have already explained you majority of the thing, but try to give you some more close-up view. Hello, I'll skip this description part. Development, research facility. So we had a students chapter. Students chapter is still we have, which was inaugurated in 2018. So journey started from 2018 about students chapter, and subsequently last year Welding Research Center. So this is the actual laboratory wherein you can see ultrasonic welding system, metals and plastic. So that was a video clip of Welding Research Center. And I think with this view, I have come to an end of my presentation. But before I close this presentation, I would like to show you another clip wherein our Honorable Prime Minister is mentioning about our university. So let me show you that small clip. And
कि आज पीडीपीयू देश ही नहीं बल्कि विश्व में भी अपनी एक जगह बना रहा है, अपनी एक पहचान दर्ज करा रहा है। और मुझे ये देखकर बहुत गर्व होता है कि यूनिवर्सिटी अपने समय से बहुत आगे चल रही है। बीते 1.5 दशक में पीडीपीयू ने पेट्रोलियम सेक्टर के साथ साथ पूरे एनर्जी स्पेक्ट्रम और अन्य क्षेत्रों में भी अपना विस्तार किया है। लेकिन अब जिस प्रकार से देश और दुनिया की रिक्वायरमेंट है, जिस प्रकार से इस यूनिवर्सिटी ने अपना रूप लिया है, मैं गुजरात सरकार से आग्रह करूंगा कि कानून में अगर आवश्यक हो तो परिवर्तन करके इसको सिर्फ पेट्रोलियम यूनिवर्सिटी के बजाय अच्छा होगा अब इसको हम एक एनर्जी यूनिवर्सिटी के रूप में कन्वर्ट करें, क्योंकि उसका रूप दायरा बहुत विस्तार होने वाला है। और आप लोगों ने इतने कम समय में जो कमाया है, जो देश को दिया है, शायद एनर्जी यूनिवर्सिटी इसका विस्तार बहुत बड़ा लाभकर्ता देश को होगा।
so that was a brief about the university, the name change and the background of the university. So with this, I have come to an end of this second presentation. Thank you, everyone. We can take questions of the earlier session and this session also.
Thank you so much, sir, for continuing your insightful talk on advanced welding technology. Your deep knowledge and expertise have greatly enriched our understanding of this important field. We truly appreciate the time and effort you have dedicated to sharing such valuable insights with us today. So, I'm requesting all participants they can ask their questions, their queries. They can unmute their mic also.
I think in the chat box, there is a question that the reinforcement material is required to preheat or not in FSP.
Yes.
Because the quantity of that material that we take is very, very small. And especially in FSP, the volume fraction that is in the form of fine powders, it has to mix with the carrier solvent. Otherwise, it is very difficult to apply in that particular pattern. I mean, the whole pattern or a slot pattern, whatever you have taken. So the powder particle has to mix with the some carrier solvent. So preheating as such, I have not noticed. Any other question?
Anyone?
Good evening, sir.
Yeah, good evening.
Myself, Dr. Devashish Sarkar, calling from Asansol, Bengal, West Bengal. Sir, you are talking about that we can use a vertical milling machine, for friction steering welding, we can make the arrangement. Is there any power limitation if it is say we are going to say join for aluminium to aluminium or like that?
In fact, I mean that Z-axis motor, that if you have at least 3 HP, 3 HP is sufficient.
Okay, 3 HP.
3 horsepower, which help
Yeah.
you to even weld 6 millimeter aluminum easily. So, but it should be vertical milling machine, not horizontal.
Okay. Thank you, sir.
VMC is required, and 3 HP probably help you to weld easily any thickness ranging from 1 millimeter, 3 millimeter, 6 millimeter.
So how you are basically controlling this someone, I mean feed, or you can say that
So machine, I mean vertical milling machine has two chart. One is for RPM chart, another one is a feed chart. So the
okay.
feed chart wherein you have the feed control, because vertical milling machine is not CNC machine. In CNC, you have a flexibility in selecting the RPM and the feed. But here you have you have a standard window, right? As per the gear setting, you have to utilize that. If you, I can, whether my screen is visible again, I mean screen is visible, right?
We are visible
Yes,
actually.
sir. Yes, it is visible.
Now you see, I have displayed one slide. You see, can you see this milling machine operating range cursor?
Yeah.
Yeah. So the machine that we have can work say 35 RPM, 48, right? And it can maximum go up to 1500. Now you see, if I want to play 1200 RPM, which is not possible, I can play either 1070 or 1500.
Yes.
Similarly, you can see the feed also. Feed is say 20, 31.5, 50, 78. Now between 500 and 800, if you want to play 600, 700, which is not possible. So vertical milling machine has this constraint.
Okay. Thank you, sir.
Okay. Any other question anybody has? I mean, we can take question from the earlier session also, if anybody has. Because that time we didn't get sufficient time. So now we have at least another 5-7 minutes available, right? So, hmm. Fine, wonderful. So it's all clear.
Sir, good
Thank you
evening,
once
sir.
again, sir.
Yeah.
Hello.
Anyone? Yes.
Yes, good evening, sir. Sorry for late asking because I was facing trouble in unmuting my mic. Sir, I have a little doubt about assisted cooling, sir. Likewise, all we know that like quenching like operations make our materials hard. So in case of steel welding, when we are getting assisted cooling, it is we are gaining on plasticity. So I am unable to understand the mechanism of assisted cooling, sir.
Assisted cooling means it is not directly submerged in the water, neither it is completely immersed into the water. So when we go for a friction stir processing, there is a dynamic recrystallization will happen. The grain refinement will take place. And then because you in aluminum alloy, many precipitation hardenable aluminum alloy, you have those precipitates. Now these precipitates also get fragmented and it will be uniformly spread into the matrix. So these precipitates plus fine grain, high angle grain boundaries all together contributes into improvement in the property. Now peak temperature, what will happen? As the temperature will grow, right? What will happen? The grain coarsening may also happen, right? With the help of assisted cooling, you are trying to reduce that peak temperature.
Yes, sir. Okay. Thank you, sir. Thank you very much, sir.
Thank you.
Sir, may I?
Please.
Sir, in friction stir welding, basically friction stir spot welding, the tool wear is more prominent. The tool material is costly as well. So how to deal with such conditions, sir, when you are processing the steels?
I mean, you're talking about friction stir welding, friction stir spot welding for steels.
Yeah, sir.
Okay. Because you are plunging and
then stirring it, and
correct.
in that particular process, the wear phenomena is more prominent. Tool wears out more often, and probably we may not get the same good amount of results as the tool is wearing at faster rate.
Yep. So maybe one possibility, we can go with some good quality coating on the tool, right? And
Okay.
the coating should
Yeah.
be such that it should not, means coating should not damage or, melt during the process, or the debris of the coating should not become part of the joint also. So if you
Yes.
can develop such coating, or maybe a special heat treatment wherein the surface properties are different. I mean, the shoulder property, the pin properties are different compared to
Yeah.
the inner. That may probably help us to say for example, we can go with the nitriding on the surface.
Okay, sir.
So
So in that
fine,
case, the cost increases a bit.
correct.
We
Yeah,
have
yeah,
tried with
cost.
tungsten
Yeah.
carbide tool
See,
as
tungsten carbide probably may become more costly, and then the machining
yes,
of tungsten carbide is another challenge. So I advise that you go with the normal H13 tool and see if you
yes,
can
sir.
go for a nitriding, and then it may help you to, have a better performance. Or
Okay,
researchers are also trying, especially even if you don't want to go with nitriding, you can think of having some cryogenic treatment of the tools. FSW tools.
okay,
If you search
okay,
for some, FSW, cryogenic treated FSW tool, you may get some more papers on that.
okay, okay. I will try,
Cryogenic,
sir.
yeah, yeah.
Yeah, thanks a lot, sir. Thanks a lot.
Welcome. Anybody else? Fine. I think with this,
Sir, I think there is one question in the chat box.
mhm. Okay.
That is laser-induced breakdowns spectroscopy and plasma welding to improve the quality and efficiency of 3D printing or not?
I'm not aware about this laser-induced breakdown spectroscopy, but certainly plasma welding I'm aware, and plasma welding has been reported for multiple applications. I mean, plasma for welding, plasma for surfacing, plasma for many applications. We have an institute for plasma research here in Gandhinagar, and they do a lot of application. But plasma welding process has been reported for 3D printing application. Plasma is reported, but I'm not aware about the one which you mentioned, the laser-induced breakdown spectroscopy. Plasma certainly reported for additive manufacture. How can friction stir welding be effectively utilized for joining the materials for varying thickness? And what adjustment in the process parameter or the tool designs required to ensure the high quality weld? Yeah, it's a good questions which is being used. I mean, dissimilar thicknesses are used mainly for automobile applications, and there you have a higher section thickness. I mean, the way we talked about advancing side and the retreating side. So depending on the thickness, the whichever is on the higher thickness, you can go with the advancing side, and the lower which will go on the retreating side. So that's how you need to select the material. The higher thickness material on the even though they are similar, I mean aluminum, the only the difference is the thickness. So you need to select them in a different position. Initially, you need to design a special, I mean, regular tool can also work, provided it, balance uh, the length of the pin in line with the both the tools, both the plates. Any other question? Fine, Manoj, I think I don't see any further question in the chat box.
Yes, sir. Sir, one more question, I think so. Dr. SK has asked just now.
Mhm. For advanced alloy composite design, which type of welding is useful? Advanced alloy composite design, which type of welding? For 3D printed part welding, I mean, it depends whether you have a you. I mean, your question is, I mean, advanced alloy and composite design. Which type of welding is useful? So you can go with solid state also if there is a problem in terms of the metallurgical challenges are there. And if it is okay, then the best is to go with the fusion welding. Researchers nowadays, they are exploring fusion welding processes and solid state welding processes for welding of 3D printed parts.
Sir, he asked micro or nano composite.
Yeah, that's okay. Means.
Another question is there.
Hmm.
LIBS enables the rapid in situ analysis of the chemical composition of the material during the 3D printing process.
So
That
he
helps.
clarified, I mean, what is,
Okay.
because I'm not aware what is LIBS. So he has given me
Okay.
some information on that.
Okay. Any questions, participant? I guess there is no. Thank you once again, sir.
Okay. I think if there is no questions, we can move ahead, sir.
Sure.
Okay. So, dear participants, first of all, I would like to thank our speaker who has taken 2 sessions continuously from the afternoon. So, thank you, Professor Vishwesh Badika, sir. I think it is really the insightful talk that you have given related to the advanced welding technology is really beneficial to all the delegates, sir. So, we thank you twice. Why? Because you have taken 2 times the session today, sir. Thank you so much, sir.
Thank you.
Okay. So I think we are taking a 5 minutes break, and we'll be updating now the feedback link in the chat box. I think many of you are asking. I request you to please adhere to this continuously. You are actually sharing this, asking the same questions in the WhatsApp group as well as in the chat box. So now we are sharing the feedback link, and this is a mandatory link. You all need to fill it, and we are giving you 15 minutes. That is near about it is 6:30. So we are opening this link up to 6:45. Now, as I have already shared in the WhatsApp group, there will be 2 links. One which we are sharing it to you in this chat box. Okay, and there will be a different link that will be actually in the ATAL portal. Okay, but that will be opened when the attendance we will be filling it for all the 6 days. Okay, so please, I request you, we are actually working on it. So please give us just 1 day or 2 days. We'll be able to update all the attendance of the attendees, and then the feedback form will be opened. We'll be filling your marks, examination marks, and then after that you will be able to download your certificates. Okay. So I request you, please, do not write it continuously on the WhatsApp group or in the chat. So we are actually sharing the feedback, and that feedback will be opening it by 6 up to 6:45, and then we'll be sharing a new link related to the examination. Is it fine? Any questions related to this? Okay, if there is no questions, we are actually updating the link on the chat. Please give us.
हेलो विश्वेश सर।
हाँ बोलिए।
Sir, any simulation software are used in friction stir welding?
I think there are software available. I mean, NC's, MATLAB. You can, they are the conventional, I mean, the regular one.
Yeah, okay, sir. But for specific welding software, any?
I don't think so any specific, but normally people have, means researchers are utilizing those softwares only.
Okay, sir.
There is no
Thank you, sir.
specific software. Yeah, means NC's, MATLAB, FEA base, all softwares they use for all kind of analysis.
Thank you, sir.
Okay, the feedback link has now been updated in the chat box. I request all the delegates to please fill this feedback link. Hello. Actually, just one announcement. What I am seeing it here is that near about 250 participants are there and only 200 have filled it. So I request you again, if you have not filled it, please fill it. Otherwise, the certificate will not be generated. Okay, so we are giving you again 5 minutes. Please fill it by within 5 minutes if you have not submitted the feedback. Okay, thank you all. We have got the feedback uh, of yours, and now we are sharing the test link. It is in the Google form. Okay, we have not uploaded that in the ATAL AICT portal. So I request you to please attempt that test on the Google form, and we will going to update your marks in the portal. Okay, so we are just sharing that in the chat box. Dear delegates, actually, we have seen that only more than 170 have filled the examination, have taken the examination. Now, just giving 2 to 3 minutes more. Please request you to those who have not attempted, please do it right now.
Hello.
Hello, very good evening, sir. I am Professor Manoj Sahani, sir.
Can you hear me? I am audible.
Yes, yes, you are completely audible, sir.
I
Sir,
am
we
Jose.
will going. Yeah,
Jose.
yeah. Actually,
Uh,
yes, sir. Sir, we're
yeah.
going to start the validatory in 5 minutes, sir.
Okay. Okay. Okay.
So actually, the delegates are taking the examination. The test is going on.
Okay. 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 Test is not over so far.
Just we are just 2 to 5 minutes behind the schedule, sir. Not more than that, sir. So it will be
Okay.
over by 2 minutes, 2 to 3 minutes, not more than that.
Okay. Okay. Okay.
Okay.
Okay.
Okay, good evening, everyone.
Yeah, good
So
evening, sir.
hopefully you all have filled the feedback link as well as the examination link that is being shared on the WhatsApp as well as on the WhatsApp group also. So we are now closing both the links. Okay. Now we're going to start with a validatory session. But am I audible clearly?
Yes, you are audible.
Okay. So before moving on, we have an esteemed speaker, the guest with us, the head of the mathematics department, Dr. Poonam Mishra Madam, the president of IIW India, Professor Joseph Phillips sir. But before moving on to both of them, I request from the participants who would like to share their thoughts or feedback so that we get to know about about the something positive and negative that we have tried our best to organize the faculty development program. So I request now from the participants, because they have taken the active participation this whole week, to speak something about FDP, what they think about it. So all are being unmuted now. So they can, just a second. You all are unmuted. You can just unmute yourself and or raise your hands.
Yes, sir. Am I audible?
Yes.
Yes, myself, Dr. Devashish Farkar, from Asansol Engineering College, West Bengal, also from Mechanical Engineering Department. So this is a very uh, extensive, very good sessions, particularly Professor Batke, Professor B. Batke, particularly in friction steering welding. This was basically absolutely very good. And all other session also very good, and particularly these two was as I am also working in some area of manufacturing. I am also mechanical. So to me, that 3D printing by Professor Dabe was absolutely very good. And uh, the other ways that the totally the selection of my topic was very good. I think so that it is this update is really got success. Thank you, sir.
Thank you, sir, for your very nice comment, sir. Thank you for your appreciation, sir.
Thank you, sir.
So I think one other has also raised their hands. Ram Manohar, sir.
Yes, sir. Good evening, sir. And
Good
thank
evening,
you
sir.
very much, sir. Thank you very much, sir, for organizing this FDP on Smart Manufacturing 4.0. And I am very much blessed to be part of this FDP because of Vishwesh sir. Sir has very much encouraged and given the insights for the new methodology in steel, FSW and steel welding. So I am very much indebted to you, sir, that you have organized such a beautiful FDP on industrialization and automation and industry 4.0, sir. Thank you very much, sir.
Yeah,
Thank you,
very
sir.
much.
So any other participant would like to say something? Miss Deepika, would you like to say something?
I think Madam probably also raised a hand. Shastra University.
Okay. Yes. Shastra. Yes. Madam, Dr. S. Rahani, madam.
University, Kanjaur,
Hello.
sir. Sir, am I audible, sir?
Yes, you are audible.
You are
ma'am.
audible. Please.
So we are having 3D printing machines and the Industry 4.0 model factory also within our campus with the Bajaj. And this is a golden opportunity as a faculty of MBA. I'm handling material management papers and OM operation management papers for the MEC and other divisions. So this is actually a wonderful session, which was given enlightenment about a lot of new methodologies. Even I'm going on, this is my third FDP, and on the same topic, I'm just, doing it. But every different topics are different. And I want some material handling, cast cutting concepts, and the additive manufacturing in the application of the other domains, so that if you might have been added it, and people like us might have been taken to the class for research oriented domains of the mechanical electronics. But anyway, it was a wonderful session, and all the sessions you have brought in the India's top second scientist, 2% scientist list person to our ATAL FTP. That was a great opportunity for us. And the other things that question and answers were answered properly by and very detailed by all the resource persons. Some of the network issues I faced it regarding the presentation, acceptance, and other things. Otherwise, everything was excellent, sir. So hats off to you, Jai Shri Ram. Thank you very much for the opportunity.
Thank you, ma'am, for the feedback that you have given to us and the appreciation. Thank you once again, ma'am. So, any other delegates, participants?
Good evening, sir.
Good evening, ma'am.
Sir, when I think I was called out and I suddenly logged out by mistake.
Okay.
So, sorry for that.
No
Good
problem.
evening, everyone. My name is Dr. Deepika Harwani, and I'm working as a lecturer at RC Technical Institute in the Department of Mechanical Engineering. And I would like to share that this was my first FDP on ATAL platform. So, being working in the government institutes, we are attending many online and offline FTP programs, and this was my first as on ATAL. So it was a very wonderful experience, and I'm lucky that my first ATAL FTP was organized by PDEU. So actually, I am an alumnus of PDU. I had completed my PhD under the esteemed guidance of Dr. Vishwesh Badheka, and he was the co-coordinator in this FTP program. So I also want to thank Dr. Vishwesh Badheka sir and Dr. Manoj Sahani sir for giving me the opportunity to share the sessions also. And if I talk about the FTP program,
Deepika, madam, I think you are not audible. Some network issue is there.
am I audible, sir?
Yes. Now you are audible.
Okay. Sorry for the disturbance. I think there is some network issue at my home. So I was saying that being from the welding domain, I had my master's and PhD topics related to friction stir welding and friction stir processing. So for me, this was like a reservoir of the additional knowledge. So I'm very much thankful. I enjoyed all these sessions, and especially of Mr. Nimesh Chenoy sir. And it was also very good to listen to Dr. Vishwesh sir again. I have attended many of his talks previously. And I would also like to add that Dr. Vivek Patel, who took the session on the friction step processing on the first day, he was my co-guide. So it was also nice to again hear him talking on the latest advancements of this process. And I also would like to thank all the team members who ensured the smooth working and the daily routine works of this FDP. Thank you, sir.
Thank you, Deepika madam. Thank you so much. Uh, is there Stephen
Oh,
sir?
good evening,
Are
sir.
you there?
Yeah, I think. Yeah, Sumit is
Hello.
there. Dr. Sumit,
Yes, sir. Good evening, sir.
good evening. Please share your feedback.
Yes, sir. It was such an amazing FDP I have ever attended. Vishwesh Badeka, sir, Nimesh Chinoy, sir. All sessions were wonderful. Even I was searching for the doubt in Vishwesh sir's session, but he was clearing all the doubts in the FDP session itself. So thank you so much, sir. Thank you so much for the wonderful sessions. And Manoj Sahni, sir, thank you so much for organizing such FDPs on ATAL platform. Thank you. Thank you so much.
Thank you, Dr. Sumit sir. Thank you so much.
Thank you, sir.
Now, Dr. Sunil Bharadwaj sir, are you there, sir?
I think with this, probably we can move further. If,
Okay. So any more would like to say something? Okay. So as we move on to the conclusion of this
you
insightful
check with
FDP,
Stephen if Stephen is there. Stephen, if he's
I
there in
think,
the. Stephen, you are there.
sir, I think is not answering.
Okay, no problem. No problem. We can move further.
Okay. So as we come to the conclusion of this insightful FTP on smart manufacturing and digital transformation in Industry 4.0, I would like to share a moment to express my gratitude to all the distinguished 10 speakers of this FDP, and approximately 254 participants have registered for this. So it's a great and really a success for this FDP. So the glimpse of this FDP I would like to share with you all. We began the session on 23rd December 2024 with a fascinating talk by Dr. Nirav Jamnapura sir from IPR, Ahmedabad, on the topic of plasma processing as a tool for green manufacturing. Then we had Dr. Ankush Sharma from Atira, Ahmedabad, who took 2 sessions on Industry 4.0 for composite industries. We were also fortunate to have Dr. Vivek Patel from the Department of Mechanical Engineering, University West, Trollhättan, Sweden, who shared his expertise on friction stir welding, a sustainable manufacturing technique. So our discussions continued with Dr. Antinlo from the University of Naples, who enlightened us on advanced manufacturing and sustainability, followed by Mr. Ravi Kumar Verma from SAC ISRO, who spoke about space and aerospace materials, present trends, and future prospects. This was being continued by Dr. Harshit K. Davesar from the Department of Mechanical Engineering, SVNIT Surat, who delivered a talk on 3D printing of composites. We were also privileged to have Mr. Nimesh Chinoy sir, Director Sigma Weld Electronics Devices Worldwide Private Limited, who conducted 2 sessions on demystifying the implementation of Industry 4.0 for welding in manufacturing setup. Dr. Ashish Shukla from Namtech New Age Education and Skills Foundation then shared his insights on the role of robotics in manufacturing and Industry 4.0. Today, also, we had 2 outstanding sessions on advanced welding technology by our one of the convener, Professor Vishwesh Badeka sir from Pandit Deen Dayal Energy University, and one from Dr. Vishal Ashok Wankhede from Indian Institute of Management, Bodh Gaya, who spoke on smart manufacturing and Industry 4.0. So we thank all the speakers who have taken their pain for conducting the 13 sessions of this faculty development program. Now, moving ahead, I would like to invite now Dr. Poonam Mishra Madam, Head, Department of Mathematics. Before inviting Madam, I would like to give a brief overview of Madam. Dr. Mishra has received her PhD degree in year 2010 in Applied Mathematics, and since then she is associated with Mathematics Department of the School of Technology at Pandit Deen Dayal Energy University. She also holds master's degree in Business Administration with specialization in Operation Management. Her core research area is study and analysis of real-world problems mathematically. This includes formulation, analysis, and optimization of the problem using different optimization techniques. She has 50 publications on her name in various peer-reviewed journals. She has also contributed 8 chapters in edited books and presented 6 papers in India and abroad. She has also delivered lectures at national and international forums. Presently, 3 students have awarded PhD under her guidance, whereas 2 more are in the process. Currently, has successfully completed funded projects with SAC-ISRO under Integrated Studies of Himalayan Cryosphere for a collaborative project for ship route optimization in sea ice areas. She is also working on another project of Giloff modeling. Now, I would like to invite Dr. Poonam Mishra Madam to address the participants. We welcome you, Madam.
Thank you very much, sir. Am I audible, sir?
Yes, yes, you are audible, ma'am.
Thank you, sir. As we have come to end of this faculty development program, Smart Manufacturing and Digital Transformation in Industry 4.0, I would like to take a moment to reflect on the incredible journey we have shared over the past 6 days. First and foremost, I would like to express my deepest gratitude to the organizers of the event, Professor Manoj Sahani and Professor Vishwesh Badeka. And subsequently, I would like to congratulate both the Department of Mathematics and Department of Mechanical Engineering for this successful event. I am overwhelmed with the speakers and facilitators from academia, research and development organizations, and from industry for their tireless efforts in making this FDP a resounding success. Your dedication, expertise, and passion have inspired all of us. Thank you very much. Over the past 6 days, on one side, we discussed and heard experts on composite and welding, and on another side, we have explored from sustainable and green manufacturing to smart manufacturing with robotics. We have learned from each other and gained new insights. I'm sure we have also formed new connections and created memories that will last a lifetime. Now, this FDP will be meaningless without its participants. So, I would like to thank all the participants for putting their trust on us, and I am sure the diverse perspectives, insights, and experiences must have enriched our discussions and learning. As we depart, I urge to carry the spirit of this FDP with you. Continue to learn, grow, and share your knowledge with others. Apply the skills and insights you have gained to make a positive impact in your communities and organizations. In closing, I offer my sincere appreciation to everyone involved in making this FDP an unforgettable experience. On behalf of both the departments, I would like to present my sincere gratitude towards our patrons, Honorable Director General of the University and respected Director, School of Technology, for their inspirational spirits. Let's stay connected, support each other, and continue to strive for excellence in whatever we do. Thank you very much. Over to Manoj sir.
Thank you, ma'am.
Thank you, sir.
Thank you for your support that you have actually given to both of the departments, because this is the FDP jointly organized with the mechanical as well as with the mathematics. So thank you once again.
The credit goes to you. You have actually worked hard.
No, without your support, it's not possible. Thank you, ma'am. Thank you so much. Okay, so moving ahead, we have with us our Director, School of Technology, Professor Dhaval Pujara, sir. So before inviting him, so I would like to again give a brief introduction about sir. Professor Dhaval Pujara, sir, brings with him over 27 years of rich experience in teaching, mentoring.
Dr. Manoj, it's not
Yes.
required.
Oh, sir.
Fine. So,
Sir,
very good
okay.
evening to all of you. At the outset, I congratulate both the coordinators of this program, Professor Deepika. At the same time, I would like to thank all the resource persons who spared their valuable time and shared insights on smart manufacturing and Industry 4.0. My compliments are also due to the both head of the departments mechanical engineering and department of mathematics, and at the same time all the delegates participants of this 6-day ATAL FDP. I was told by Professor Badeka almost every day that the average presence for this FDP was around 175. That shows the success of the program. I would like to urge all the delegates. This is a wonderful platform. You got an opportunity to connect with 175 stalwarts of the country. So I urge to all of you, please remain in touch, share your expertise, thoughts, ideas amongst each other. That will ultimately help to the country. It will also help to the students also. Once again, I thank the university management, both the coordinators, both the HODs, and all the participants. It is my wish that both the coordinators should come out with new ideas. For example, we may have a similar kind of FDP on Industry 5.0 or maybe robotics in time to come. These are the areas in demand where this kind of collaboration, discussions, interactions are required. Once again, thank you everyone who has contributed to this wonderful FDP. Thank you so much.
Thank you, sir, for your kind and encouragement word. I think it will be a great help to all the faculties of Department of Mathematics and Mechanical Engineering. Thank you, sir. Thank you so much, sir. So, moving ahead, I would like to invite Professor Vishwesh Badika, sir, to introduce our next guest, that is President IIW, Professor Jose Philip, sir. Sir, over to you, sir.
Yeah. Thank you. Thank you very much, Dr. Manoj. As you know, this particular FDP is in collaboration with IIW India. And about 1.5 years back, there was a formal MOU was signed between IIW India and PDU to strengthen the welding research activity. So as a part of this particular proposal, it was submitted with the IIW India. And we have with us Mr. Jose Philip. He is the current president of IIW India. So without taking much time, I request Jose Philip sir to kindly address your thoughts, your views. Please, sir.
Yeah,
Hello, sir.
very good evening to you, Dr. Badeka,
Thank you, sir.
Professor Manoj Saini, Madam Poonam Misra, other learned professors, faculties attended as delegates, and I'm very happy to be in your midst in the closing ceremony of this 6 days faculty development program organized by AICT. It is sponsored 1 week faculty development program. It started, I understand, the program started 23rd and ending today. It is organized by Department of Mathematics jointly with the Department of Mechanical Engineering, School of Technology, Pandit Deen Dayal Energy University, Gandhinagar. The topic was very attractive, smart manufacturing and digital transformation in Industry 4.0. As they explained here, it is very encouraging that about 170 delegates attended, and finally there is an assessment examination. As the president of IAW India, are you all well aware that we are in the process of promoting welding technology in the country, which will encourage or motivate industry in the country for our economic development. Accordingly, I'm very much happy that such program will definitely help the faculties, because what Professor Badeka and Professor Manoj are doing, they are bringing new development in the welding and distributing for other faculty members, which is very frequently it is required, because I think most of the people, the feedback I got, many people got benefited by this as a learning process, because very, very important job you are doing for helping the faculty, because all on a sudden all are getting the new information about especially friction stir welding, additive manufacturing, robotics. These are going to be the business of welding industry in the country, which the new technology has to be brought to the industry. That is why we will achieve the productivity in the manufacturing, and especially there's a topic called smart manufacturing, because we have to do a lot of things, avoid wastage, increase productivity, motivate the human power. These all are required. So such type of programs are very much relevant in our midst. So in that way, I am very, very happy that you people are putting lot of efforts to bringing technology among the faculty, because as you know, no, it is directly going to the students. That is a very encouraging information which I am getting. So I am very happy. And of course, Professor Bedeka is our part and parcel of IAW. He is very active. I am not telling, I need not tell about his activity and capability. Many kind of things are doing in even we met last month, even December, we met at Jamshedpur, where he has made a lot of presentation, technical presentation in the National Welding Seminar at Jamshedpur. And also he is heading our student chapter as the student chapter chairman. So these are the efforts he is doing. Along with such type of good program, I also expect such program should be periodically conducted, so now you are selected online. Online meeting is it is very economical, need not travel, need not spend money for travel. So these are the convenient, and also you have structured this program every day 2 hours, no? Oh. So such things can be conducted even in the future also. So I appreciate the efforts of the team, efforts of the Professor Badeka, Professor Manoj Saini, and Dr. Madam Poonam Misra, all people behind this. So once more, I congratulate you for conducting this program, and also congratulating all the members attended this FDP program, faculties. Thank you. We will meet next time also. Thank you, Professor Vedaka, for inviting me. Thank you, Manoj Saini, to
So you're
invite
most
me for
welcome.
this.
Thank you so much for coming, sir.
Yeah, thank you.
Thank you very much, sir. Thank you very much, sir, for sparing your valuable time, sir.
Yes. You know, I am sitting in the southernmost tip of our country. I am in Cochin.
Correct, sir.
So we could connect. That is the technology, another development. So we could interact with you. It's a very fine moment for me. Thank you.
Yes, sir. Thank you very much, sir. Thank you, sir. Thank you very much, sir, for your insight and views on our faculty development program, sir. Over to Dr. Manoj.
Sir, you would like to say something, Badika sir?
No, I mean, I'm just thanking Joe sir for sparing his valuable time and sharing his views on our faculty development program. So now over to you, Dr. Manoj.
Okay, thank you, sir. Thank you, sir, for the insights that you have shared, sir. Thank you. I think the enlightenment that is being shared with by the speakers to all the participants will be passed on to the students. What Joseph sir has said. Thank you, sir. Thank you. So we are approaching towards the end of the program. So on behalf of the organizing team, I would like to thank AICT for giving us an opportunity to organize this faculty development program and sponsoring it. I would also like to thank the PDU management, Honorable Director General Sir, Professor S. Sundar Manoharan Sir, Honorable Director School of Technology, Professor Dhaval Pujara Sir, Dean of School of Technology, Professor Surendra Kachwaha Sir, heads of both Mathematics Department, Dr. Poonam Mishra Madam, and Head of Mechanical Engineering Department, Dr. Jatin Patel Sir, for their kind encouragement and support. I would also like to thank the faculties, research scholar, junior research fellows, and staff of both the departments. I would also like to thank the admin department, amenities, whole School of Technology, and all those who are directly or indirectly connected with this faculty development program. But above all, special thanks to all the participants who have spent their invaluable time and their active participation in this 1 week faculty development program. At the end, I would like to thank Professor Vishwesh Badeka sir, whose continuous support has made this FDP possible. So thank you so much, sir. I would also like to thank Mr. Dharmik Chauhan for being continuously working with us to make this FDP a success. So thank you, Dharmik. So I would like to thank again the management of PDU, AICT, all the participants, the staff members, faculties of both the departments, and a heartfelt gratitude to each one of you. So with this, we conclude this faculty development program on smart manufacturing and digital transformation in Industry 4.0. So thank you all for being a part of this enlightening experience. Wishing you all the best in your future endeavors. But before ending, I would like to make an announcement that we are getting a lot of queries regarding to the attendance. I request all the delegates will be updating your attendance in the portal, I think in a day or two. So please be patient with us and uploading all your marks in the AICT ATAL portal. After that, I request you to please fill up the feedback form in the AICT portal. After that, you will be able to download your certificates. So thank you. Thank you all.
Thank you, everyone, and thank you. Jai Hind.
Thank you, Jai Hind.
Jai Hind. Jai Hind, sir.
Thank you.